We have previously seen that when I have a conductor and we apply an external electric field, we start getting an induced charge on one surface and opposite induced charge on the other surface of the conductor. So we would create some surface charge density on these surfaces. And we had also qualitatively seen that the total electric field which is going to be present is going to bend such that it hits the conductor at 90-degree angles. Let us now try to quantify what the relationship between this electric field and this charge will be, and also prove mathematically that there will not be an electric field which would be parallel to the conductor at that boundary. And again, remember, electric field inside is 0. This relationship between electric fields and charge densities are known as the boundary conditions. What are the rules electric field and a charge density have to obey, and which direction can electric field be present? So what we are going to assume is that we have a conductor, and I've just gone to one point on the boundary, so every below is a conductor. And for the time being, let's assume that there is electric field which hits the conductor, and I'm arbitrarily drawing it to hit into the conductor. Because of that, I would start inducing some negative charges and create a surface charge density. So there are two boundary conditions. One is going to be related to this component of the electric field which is hitting 90 degrees onto the conductor, and we're going to call it the normal component. And the other one is a component which is parallel to conductor ET. And this is what we call tangential component. Previously, we had argued that this tangential component has to be 0. Otherwise, the electrons which are present on the surface, and they would start to move, creating an opposite induced field, and that would happen till the tangential component goes to 0. Let us now prove it mathematically or physically. So we have this conductor sitting in air, and let's look at what is known as the tangential boundary condition. I have said that for the time being, we are assuming that there is a tangential component, but we have also said that was the first rule we defined, electric field inside the conductor has to be zero. This tangential field, which I am assuming, is happening in the air. So the way we can try to prove this is let's start from a point A. We are going to walk to point B some distance delta L. Then we are going to get into the conductor, walk back, let's call that point C, D, and we are going to walk up again. And let's say we walk a height of delta H. So we start from A, we walk all the way across that loop till we come back to A, and what I am interested in calculating is what is the delta V as I go from A to A. So I've started from one point. What is the potential difference I would create as I come back to the same point? And we know potential is, or electrostatic potential is conservative. So if I come back to the same point, I walk on a hill and I come back to the same point I start, I should not have changed my potential. So delta V A to A should be 0. We have electric field present on the top, and from A to B, this delta V A to B is going to be A to B plus B to C plus delta V C to D plus delta V D to A. When I'm going B to C, electric field is in this direction. I'm walking downwards, that is 90 degrees. So this is simply 0. E dot dl would be 0. When I walk on this path, electric field inside is 0. I add those zeros up many, many times. I still get a 0. So that would be 0 too. And from going from D to A, I have the same argument as going from B to C. Electric field, if electric field is present, it would be in that direction, and I am walking perpendicular to that at 90 degrees. So this would also be 0. However, when I am walking from A to B, I am assuming that there is electric field present, and I'm walking in the direction of electric field, so I would get E T delta L. That would be the potential difference when I walk from A to B, and we have already argued that this should be equal to 0, which now proves that this tangential component of the electric field cannot exist. E tangential has to be 0. We had previously made this argument based on just physical understanding of how charges would distribute itself. Now we have done a pure mathematical proof, and there should not be any doubt left in our minds that when I have an air conductor boundary right at the surface of the conductor, there is no tangential electric field even in air. Okay? This field, even in air, right at that boundary, has to be 0. The only field that can exist is a field which is normal. Let us see what the normal boundary condition is. So normal boundary condition, as I have drawn it. So at the bottom I have a conductor, and I have air on the top, and there is electric field, and I'm drawing the electric field hitting into the conductor. So there must be electrons which are created on that surface, and that would be the surface charge density. The normal boundary condition describes how E normal and rho s are related to each other. This charge density and the electric field, again, remember we had previously said charge is the source of electric field. So the strength of electric field would depend upon the charge, or if I have electric field coming from outside, it would induce a charge, and that relationship would always have to be maintained. To figure this relationship out, let's go back to our friendly Gauss law. And what we're going to do, again, I'm assuming planes, so this conductor is very large that way. And we are going to make a Gaussian pillbox of a very, very small height. So we are right at the surface. We know electric field inside is 0, and as I have drawn it, we have electric field En coming in, and your ds on that surface would be going out. And let's assume that this cross-sectional area is A. So applying Gauss law, we get E normal times A minus of that, because E and ds as I have drawn are opposite directions to each other. Angle between them is 180 degrees. So cos is a minus 1. So we get a minus E and A. The flux on this part is 0 because electric field is 0. The flux on this part is 0 because ds is pointing in that direction and E normal is pointing downwards. That has to be equal to the total charge which is enclosed. The total charge which would be enclosed, we have already previously said that the charge is only sitting on the surface and there is no charge in the volume of a conductor. So the total charge which is enclosed is the charge which would be enclosed within that region of the surface, which would be rho SA times epsilon naught. And it tells you E normal in this case would be minus rho s by epsilon naught. This is your tangential boundary condition. If your electric field is incident onto the conductor, or if your charge is negative, then the relationship is En is always going to be minus rho s by epsilon naught. Or if the field was going out of the conductor, then the charge here is going to be positive. In that case, E normal is going to be rho s by epsilon naught. If you know one of these two values, then you know the other two. Let's say you put some charge, you put a charge rho s on the conductor, and you want to calculate what the electric field is going to be. Right at that boundary, the electric field would have to have that relationship. Or in another case, you created an electric field externally. So this electric field was created externally and it hit the conductor. What charge would it induce on the conductor would also follow this relationship. So E normal magnitude epsilon naught should be always equal to the magnitude of rho s. If electric field is hitting into the conductor, rho s would be negative. If electric field is leaving the conductor, rho s would be positive. These form the boundary conditions for a conductor. We will use these boundary conditions when we start knowing our first device, which is capacitance. And we will see that in another couple of weeks. Keep these in mind because when we start calculating capacitances, we will be using these boundary conditions to write our fields and charges very, very quickly.